In this lecture, let us talk about slope detection. If you remember from the previous lecture that we discussed frequency discriminator, so where we used two bandpass filters. Okay, so these two bandpass filters motivated by what? What do we really want? We want a differentiator. Therefore, the bandpass filter is motivated by a differentiator. That means we wanted to realize the differentiator through a bandpass filter. So approximately the differentiator characteristics to be available around the carrier frequency. Okay, so if you have a filter response like this, if you take this portion, it has linear characteristics. Okay, so the j omega characteristics that we wanted to shift them to the frequency of interest, that is the carrier frequency. So really speaking, initially let us look at only one filter. See, we had two filters like this, right? Two filters. Now let us take only one filter and derive its mathematical expression. Now this filter has the frequency response, let's say h1 of f. Okay, so h1 of f. Now I am going to take this linear portion, this portion alone. So that I am going to draw like this linear portion. Okay, and this one is let's say carrier frequency fc plus capital B suffix t by 2, and this point is fc minus b suffix t by 2. What is bt here? bt is transmission bandwidth. Okay, so ideally we wanted a filter characteristics like this we want ideal characteristics. So let me call it h1 of f divided by j. Okay, from a single slope detector, this is the kind of thing that I want. So remember, I want a j omega kind of thing. Okay, that is differentiation. So that's why I am plotting h1 of f divided by j. Your thing is h1 of f is j omega times your function h, input Fourier transform of the input function. So you take this j to the denominator. So h1 of f divided by j is equal to omega times something. Okay, so if you recall, you have a differentiator. Input is x of t and its impulse response is h of t, output is y of t. What is y of t? Y of t is h of t convolved with the x of t. Okay, now what is y of t? Y of t is differentiated version of the input, right? That's what we are saying now. You take the Fourier transform of that. So your output y of t is equal to d by dt of x of t. Now take the Laplace Fourier transform of x of t, you will get x of j omega. In the output, y of j omega is j omega times x of j omega. Okay, now y of j omega divided by x of j omega is equal to j omega. Now this one is nothing but Fourier transform of your h of t. So that is denoted by h of j omega. h of j omega is equal to j omega. So h of j omega divided by j is equal to omega. Now what is this? Linear function of the frequency. h of j omega is equal to omega. Okay, so that is why we are plotting. Instead of omega, I am using the frequency f notation, h1 of f divided by j. That is how this j has come now here. So this is a single loop detector. This is the kind of thing that we would like to have. Okay, now what you will get on the left hand side. So this is my positive frequency, because we are talking about real system. Real system means it has equal contribution, same contribution in the negative side also. Therefore your system response would look like this. like this. So this one is minus fc minus b suffix t by 2, and this one is minus fc plus b suffix t by 2. Okay, here your b suffix t is transmission bandwidth of the FM signal. Okay, and this one is idealized filter that we have served my purpose, corresponding to one of the two bandpass filters. Now, any of the two bandpass filters I am trying to realize, okay, this kind of characteristics. I have two bandpass filters, right? Bandpass filter 1 and bandpass filter 2. So let us try to realize any one, either take bandpass filter 1 or bandpass filter 2, doesn't matter. Okay, at the moment let us work out with the case of single bandpass filter, then we will idealize this for the other case also. Therefore, this idealization is for the case of when we are using a single bandpass filter like this. So we are taking this linear region. But really speaking, the portion of the bandpass filter response which I am effectively trying to utilize is this linear region. Okay, and I am idealizing that as if I have a filter with these characteristics. Okay, these characteristics and these characteristics. Basically, therefore, we need to analyze the behavior of this filter. Okay, this filter followed by an envelope detector. Recall from your previous lecture, we have bandpass filter followed by envelope detector. Okay, for your FM discrimination. Okay, because we don't need to look at the complete behavior of the bandpass filter. Okay, so I don't bother what is happening in this region, and I will not bother about in this region. I need to consider only this portion alone. So we are not going to use the characteristics of the bandpass filter beyond this point. Let me say that point is peak or hump. Beyond the hump, we don't worry. So we are representing the rest of it by a linear approximation of this kind, this line, green color. This is a linear portion. So this is what ideally important if you want to use a single bandpass filter. Now, how the picture changes when you are using two bandpass filter, that will take up subsequently. Okay, so what all I am saying is that this approximation that I would get is in the linear region. If I want to use a single bandpass filter based system, which we discussed earlier, then I should get the zero response at this point. This point I should get the zero response. But I am not getting zero response, right? This is non-zero. So that is why we went to two bandpass filters. Okay, so let's first discuss the single bandpass filter or single slope detector output. So you have a single slope detector or demodulator here. So this is single slope detector or demodulator. Then later on we will extend this to the two slope detector. Now let us represent these characteristics mathematically. Okay, so this characteristics, this color represent this filter by its complex envelope. So I have in the positive side I have like this, in the negative side I have like this. So now let us represent this guy in the complex representation. I mean complex envelope. So if you bring to complex envelope, it comes to your baseband. So it will be like this. This is minus b suffix t by 2 and this one between b suffix t by 2. Okay. Now let us assume here the slope is equal to 2 pi a. I am arbitrarily choosing some value. A is some arbitrary value. Okay. Therefore slope is equal to 2 pi a. Okay. This 2 pi is just arbitrarily selected. The moment you bring back to your envelope, complex envelope, then this slope becomes, because this is coming over here and this guy also coming over there. Therefore 2 pi a plus 2 pi a, it becomes 4 pi a. The slope becomes 4 pi a in the complex envelope, where a is a constant. Okay, therefore the amplitude gets doubled in the baseband. Here amplitude gets doubled when you consider the complex envelope. Okay, so when you consider the complex envelope, the amplitude gets doubled because one is coming from the positive frequency side, this guy is coming to this portion, and this guy also coming over there. Therefore the amplitude will be doubled, so that is why your slope becomes 4 pi a now. Okay, I am going to use complex envelope representation of both the FM signal as well as this filter. Okay, so this is my filter H1 of f by j. So let me represent the filter response as well as my FM signal in the frequency domain. Complex envelope representation. So that the manipulation will be very easy. That is the only reason we are going for complex envelope representation. Okay, otherwise the manipulation will not be that much easy. Okay, so why are we doing this? To study the response at the output of the filter. Now what I want to mathematically represent in this picture is, what we are saying is the complex envelope representation in the frequency domain is, let me denote by H1 of f. Okay, and that one is 4 pi a. Okay, therefore, and this one is called a slope circuit, and no longer call it a bandpass filter, because bandpass filter has the complete characteristics like this. But this is not a bandpass filter, no more bandpass filter, it is a slope circuit. Okay, which of course practically you realize through bandpass filter, even though you call it as a slope circuit, but this circuit is realized by using your bandpass filter. Okay, you realize it through a bandpass filter, and this one I am denoting by H1 tilde of f. Your bandpass filter is denoted by H1 of f divided by j. Look at here, and this one is H1 tilde of f, and this H1 tilde of f is equal to j times 4 pi a. How do you represent this mathematically? It's a slope function, right? So if you write mathematically using a slope formula, x1 y1 and this one is x2 y2, then you can write f plus bt by 2. Okay, so this is the math. I don't think that I need to explain this equation. So this comes from your signals and system. Please recall how we can write this. Okay, no need to memorize it. Okay, this is the equation of a straight line. So this is a straight line. The straight line at when f equals fc, its value is how much? You can find out from the straight line. At minus bt by 2, it is 0. At plus bt by 2, its value is 4 pi a times that frequency. So the equation of the straight line can be written as j times 4 pi a times f plus bt by 2 in the range between mod of f lying bt by 2. Okay, so this is the complex envelope representation. Okay, at f equals minus bt by 2, this guy becomes 0, and at f equals plus bt by 2, this guy becomes 4 pi a b suffix t. So let me write down this complex representation of H1 of f. This is called a slope circuit. It is no more bandpass filter. Of course, the slope circuit is realized by bandpass filter, but now we are calling it slope circuit. Is equal to, this is denoted by H1 tilde of f, which is j times 4 pi a. It is a straight line equation. F plus your 10th standard mathematics bt by 2 in the frequency range mod of f less than b suffix t, and 0 mod of f is greater than 0. That's it. So this is the mathematical representation of the complex envelope of the slope circuit, okay, that I am using here. So what is the input that you are feeding into this bandpass filter? You have a bandpass filter 1 and its response is h1 of f, and this h1 of f equivalently we are representing this h1 tilde of f. What is the input to this guy? The input to this guy is our age old friend frequency modulated signal. Okay, so the input that you are feeding into this bandpass filter is your FM signal. So your FM signal x of t is equal to AC times cosine of 2 pi fct plus 2 pi kf integral of m of tau d tau. This is my FM signal. Now let me write down this frequency modulated signal into its complex envelope. Okay, so the complex envelope, let me denote by x tilde of t. X tilde of t is equal to AC times exponential of, when you write in the complex envelope form, the carrier term will go away. Okay, so this will not come because you are bringing back the spectrum from the carrier frequency to your zeroth frequency, so this will go to 0. Okay, so therefore this is going to be j times, if you have some difficulty in this complex envelope, go to the previous lecture, okay, where we discussed elaborately about a complex envelope representation of a bandpass signal. See, this FM is a bandpass signal. Okay, so that bandpass signal we are representing in terms of complex exponentials. Integral of minus infinity to t m of tau d tau. This is the complex exponential. Okay, now if you take Fourier transform of this, then you will get a capital X tilde of f. Okay, let's say this x tilde of t has some spectrum and the spectrum is denoted by x tilde of f. So this is a time domain description and this one is frequency domain description. Both are same. Okay, so therefore Fourier transform of x tilde of t is the x tilde of f. Now let us not try to find out the Fourier transform of x tilde of t. Let us just assume that the Fourier transform of x tilde of t is x tilde of f. Therefore you have bandpass filter 1. Its complex envelope representation is h1 tilde of f and the input is x of t, but in the complex envelope notation it is x tilde of t. In the frequency domain it is capital X tilde of f. What is the output? Let me call the output is let's say S1 tilde of f. Okay, just I am not notating, giving some different notation. So S1 tilde of f denotes the output. So what is output? In the frequency domain, this guy and this guy both are getting multiplied. So therefore x tilde of f multiplied by h1 tilde of f. In the time domain both are convolved, but in the frequency domain it is simply multiplication. Recall from this from your signals and system. Okay, so if you multiply these two guys, that will give the complex envelope of the output spectrum. So this is complex envelope of the output spectrum, and this one is complex envelope of the input signal. What is your input signal? FM signal. And this is the complex envelope of your bandpass filter. So everything we are talking in terms of complex envelope. Simply you multiply the input signal with the complex envelope of your bandpass filter. Therefore your S1 tilde of f is equal to x tilde of f Now by the way, what is h1 tilde of f? Just now we got its mathematical expression. Where is it? This one. You substitute here. J times 4 pi a One second, I did some mistake, I think. Okay, j times 4 pi a. Okay, let me rewrite this expression. Is this correct? Hold on. Okay. I think there is some small mistake. I think this is not 4 pi. I think this is 2. Check this, okay. J times 2 pi a times f plus bt by 2. So, and this also. Write down the equation and you can get the answer. J times 2 pi a times f plus beta by 2. There is a 2 here, it is not 4. Okay, check this whether 2 or 4. I guess 2 is the correct answer. J times 2 pi a multiplied by f plus beta by 2. Okay, now you take this guy inside. So j times 2 pi a x tilde of f times f, okay, plus 2 will get cancelled. J times pi a b suffix t times x of f, x tilde of f. This is what you get now. Now if you rearrange this, then it is j times 2 pi a f times x tilde of f plus j times pi a b suffix t, and the 2 will get cancelled, b suffix t and x tilde of f. So this is my output of bandpass filter in the frequency domain. Now take the inverse Fourier transform of this equation. If you take inverse Fourier transform, let me denote small s1 tilde of t, which is equal to, what about this one? What do you think the inverse Fourier transform will be? You are multiplying f with the Fourier transform. So this is differentiation in the time domain. Okay, so this 2 pi and f you can write as omega. 2 pi f you can write as omega. So j omega. Therefore, the whole thing I can write as j omega times a. Let me write a times j omega times x of j omega like this. So this is what differentiation property. So this becomes a times d of x tilde of t. I'm sorry, small x tilde of t by dt, differentiation of the complex envelope of the signal in the time domain, plus j times pi times a times b suffix t this is x tilde of t. Okay, so this is the corresponding time domain equation at the output of your bandpass filter. Okay, so I have expressed the output in terms of the input. Input is differentiated once and added with the another signal x tilde of t. Now let us think a little more about this equation. So now what do you find from this equation? Let me say equation number 1. Now this is my output. Output is the sum of two things. The first one is input itself. This is my input. okay, plus the derivative. So output is input itself plus the derivative. Okay, therefore S1 tilde of t is equal to, you take a commonly outside, d times x tilde of t by dt plus j times pi times b suffix t x tilde of t. So let me call this as equation 2. So this equation 2 shows that the circuit, slope circuit, like this, the slope circuit that I have started with carry out the differentiation that I wanted to carry out. So therefore this circuit differentiates your input signal. Okay, but in addition to the differentiation, I have one more additive term here, this extra term. This is fine, this is what I wanted. Okay, but this guy I don't want. So somehow I need to remove that. So that is not an issue. Okay, so this is my bandpass filter. I am taking this bandpass filter as a slope circuit because I am considering only a linear range. So once you write down the mathematically, then you are getting the equation like this, and from this you can say there are two terms. The first one is differentiation of the input signal, that is what we want, plus we are getting one more term, bonus term, but that we don't want, some additive component. Now let us substitute for x tilde of t. What is x tilde of t? If you go back, that is complex envelope of your frequency modulator signal. It is here. This is your x tilde of t. Okay, so x tilde of t is equal to AC times exponential of j times 2 pi kf integral of m of tau d tau. Now you differentiate with respect to time. If you differentiate this, what will you get? Dx tilde of t divided by dt, which becomes exponential. So AC times j 2 pi kf, this becomes m of t. Again e to the same guy, j 2 pi kf d tau. Okay, now let me call this as equation 3. Substitute this 3 in equation 2. Okay, so substitute equation 3 in equation 2, and equation 1 also you can, no, let me say this is equation A, and this also you can substitute in equation 2. Then your S1 tilde of t, if you simplify this, I am writing the final expression. Okay, so the final expression is j times pi times b suffix t small a capital AC 1 plus 2 kf by bt times m of t multiplied by exponent of j times 2 pi kf integral of d tau. This is what you get finally. Okay, and you are looking at the output of the envelope. Okay, how is the real envelope related to the complex envelope? Just take the magnitude of this. Okay, what we want is, see, this is the output of my bandpass filter. The bandpass filter is given to the envelope detector. Envelope detector will give you the magnitude, right? So real envelope will be obtained by taking the magnitude of this. So therefore take the magnitude of this. So S1 tilde of t, take magnitude, then this is going to be, if you take the magnitude, then it becomes pi times b suffix t a times AC multiplied by 1 plus 2 kf by bt m of t. Okay, this guy will go away. So you get the envelope of the output which is proportional to the message signal m of t. The message signal m of t plus some DC component. This is my DC component, same as before that we discussed. So this is the analysis of single slope circuit. Analysis of single slope circuit, because we consider only single bandpass filter. Okay, so now we will consider how the things will change if I take two slope circuits, I mean second slope, that means two bandpass filter. Okay, so the purpose is to get the balanced demodulator. Balanced demodulator in the sense, like at FC, at F is equal to FC, my YD of t detector output must be equal to 0. That is the condition. So the circuit which gives this kind of condition is called a balanced demodulator. Okay, so that is the main purpose. So the purpose of the balanced discriminator is that the output of this balanced discriminator should be equal to 0 when the frequency F equals FC. Okay, so that 0 or DC response of the FM signal is maintained. Okay, so this one is the complex envelope of the output. Okay, as you can see, magnitude. Okay, no, I'm not complex. It's a magnitude. Okay, I'm sorry, this is wrong. This one is a complex envelope. This one, that I'm sorry. This one is a complex envelope of the output. So if you take the modulus of this, which represents the envelope of the output waveform, which is given by pi times b suffix t times a times ac, 1 plus 2 kf divided by bt times m of t. Okay. So this is the expression for expression for the output in terms of the input signal. Okay, our input signal is m of t. Okay, let me call this is equation 4. Now as you can see, equation 4 shows that output envelope of the circuit is dependent nearly on the input message signal m of t as we want. Also it has a DC component. What is a DC component? 1 times this pi bt and AC. Okay, but that DC component we don't want. Basically the same thing that we physically argued earlier in one of the lecture, that the slope circuit converts the FM signal or angle modulated signal into an amplitude modulated signal, AM signal. Okay, so therefore equation 3, where is it? Not this one. Let me say this is equation 4 and this one is equation 5. Okay, therefore this equation 5 indicates amplitude modulated signal. Okay, and if you multiply 1 by this one, that represents the carrier. Okay, the only thing is that in this case the carrier is not a constant frequency, the carrier is variable frequency, but the carrier itself is an FM modulated signal. Okay, this and all I discussed elaborately in one of the previous lecture. Okay, just I am recapitulating here. Okay, so we have seen that the envelope detector is nothing but a diode followed by an RC circuit. It hardly matters whether the carrier has a constant frequency or whether the carrier has carrier phase keeps on varying. Okay, so envelope detector is insensitive to the carrier frequency or phase. The operation of the detector is essentially based on detecting the peaks of the carrier, envelope of the carrier. So it tries to track the envelope detector tries to track the peaks. Okay, and it won't matter whether the time cycle comes close together or cycles are slightly far away from each other. Okay, you have the signal like this, whether the cycles are very close by like this or sparsely like this, it doesn't matter for your envelope detector. Now what we can do to take care of the fact that there is a DC component, to take care of this DC component is, this DC component is that which we didn't want in fact. Okay, so what can we do is we will take the another slope circuit with somewhat different characteristics than the slope circuit, with this, so that this DC component can be balanced out. So that's what we need to do now. The same analysis we will repeat, but slightly different fashion. So we want to balance out the response at the carrier frequency, but at present at carrier frequency my response is not 0. Okay, so in this case we had the circuit like this. This is my H1 of f. Now if you find the complex envelope, it has like this H1 tilde of f. This is by j. Okay, here the slope is 4 pi a, and this is b suffix t by 2 minus b suffix t by 2. This is my frequency. Okay, this we already know, we discussed now till now. So what should we do to balance this out? All we need to do is the following. We take a mirror image of this. Okay, so the mirror image will be like this. You take the mirror image of the circuit like this. So this is minus bt by 2 and this one is bt. So that means this is, let me say, H2 tilde of f, and this one is H1 tilde of minus f, just a mirror image of the first band pass filter, which is like this. Okay, therefore H2 tilde of f is equal to H1 tilde of minus f. Therefore if you subtract these two guys, this point and this point both are same, therefore you don't get any value at the frequency f equals 0. So if you do that, the slope instead of being 4 pi a, the slope varies minus 4 pi a here, minus 4 pi a. So the ultimate goal is we want to make the response to 0 when the frequency is 0 at the origin, or if it is modulated then it becomes, it should be 0 at the carrier frequency. That is why we are doing all those things. Therefore H2 of f is equal to H1 tilde of minus f. We know H1 tilde of minus f. Take that expression and replace by minus signal, that's it. So the exact relationship, okay, exact derivation whatever we did earlier. Okay, so the same circuit and same thing, but only the frequency will be changed to minus f. So we will proceed the analysis with this kind of slope circuit, in our mind. Okay, this is my second slope circuit. Okay, so therefore my second slope circuit is this one. So this is you recall your H1 of tilde of f is equal to j times 2 pi a f plus b suffix t by 2. Now this one becomes j times 2 pi a, f will be replaced by minus f, that is why I put minus here, minus symbol, plus b suffix 2 by 2. This is H2 tilde of f. So you see the actual filter is a bandpass filter, and this one is a complex envelope representation of that. Okay, therefore this is a low pass representation at low frequency, how the representation is. Yes. Okay, now this is your H2 tilde of f. The input is x tilde of t in the frequency domain, x tilde of f, and I am getting the output. Output is the multiplication of these two guys. This is the second slope circuit. Let me denote this second slope circuit. Output is s2 tilde of f. This is equal to, because you are doing the multiplication in the complex domain, therefore this is 1 by 2 times h1 of f tilde of times s tilde of f. I think again I have done the mistake. Okay, let me go back and correct that. So where is it? I think here I have done some mistake. Okay, let me correct that. What did I do? Yeah. I think this one is 4 only. Okay, this one is 4 again. Therefore, here also it is 4, and but before there will be some 1 by 2, because it is a complex multiplication. So when you take complex multiplication, that factor 1 by 2 will come. Okay, that I did not consider here. Okay, so this is 4, and that's it. So then you'll get, then the answer is correct. Okay, so if you multiply 1 by 2 to here, then you'll get j times 2 pi a. So let me write this, j times 4 pi a. That's right. So this one is again wrong. It is 4 pi a. Okay. This also 4 pi a. That's it. Fine. I am sorry for this little confusion. So this is a formula. Okay, it is not like normal frequency multiplication, it is complex multiplication. So that is why this 1 by 2 factor has come here. Now substitute this, all these guys. You know h1, I'm sorry, why did I put h1? This is h2, right? I'm sorry, h2 tilde of f times s of f, not s of f, x tilde of f, because the input is x tilde of, it is multiplied here. Okay, therefore s2 tilde of f is equal to 1 by 2 h2 tilde of f times x tilde of f. So this is 1 by 2 h2 tilde of f is h1 tilde of minus f times x tilde of f. So this is, we know h1 tilde of minus f, you substitute everything, finally you will get a times, you take inverse Fourier transform, then you will get I am writing the final answer. Okay, so same process, s2 tilde of t is equal to minus a times d derivative of x2 x tilde of t by dt plus j times pi times b suffix t x tilde of t. Okay, this will remains with the positive sign and this will becomes negative sign. So finally, if you include the carrier component x2 tilde of t, then you take the magnitude, I mean differentiate, because x2 tilde of t is what? It is AC times exponential of j times 2 pi kf integral of minus infinity to t m of tau d tau. So differentiate once and substitute here, and then final expression I am writing here, s2 tilde of t is equal to j times pi b suffix t small a capital AC multiplied by 1 minus 2 kf divided by b suffix t times m of t multiplied by exponential of j times 2 pi kf integral of m of tau d tau. Now you take the magnitude because we need envelope. So if you take, because this guy is given to envelope detector, the output of the envelope detector is your magnitude. Therefore s2 tilde of t, you take magnitude, then this becomes pi bt small a capital AC multiplied by 1 minus 2 kf divided by b suffix t times m of t. If you take magnitude, this exponent part will go away, will become 1. Okay, so this is my s2 tilde of t. Now what do I need to get to balance it out the DC term? Right, all I have to do is subtract the two outputs. So I have s1 tilde of t magnitude, and that one we know, and then my final output yd of t is equal to s1 tilde of t magnitude minus s2 tilde of t, right? So that's it. So in the overall balanced FM discriminator becomes then a dual slope circuit. Therefore you have a band pass, let me say slope circuit 1, slope circuit 1, then followed by envelope detector 1. Okay, and this one is s1 tilde of t, and this one is mod of s1 tilde of t. The same signal is given to slope circuit 2, then here you will get a s2 tilde of t and envelope detector 2, and the output is s2 tilde of t magnitude. Now what you do, you subtract s2 tilde of t from s1 tilde of t. So this is plus and this is minus. So the output is s1 tilde of t magnitude minus s2 tilde of t. So that's the mathematical theory behind the balanced discriminator. So as you can see, the balanced discriminator that we discussed earlier essentially tries to realize this figure. Okay, so remember we have two tuned circuits. I mean two bandpass filters. Okay, one which was approximating one slope circuit and the other which was approximating the other slope circuit. That's all that we had. Okay, and that's what this mathematical theory now precisely explains. Okay, precisely explain why the difference in the envelope of the two would be your recorded demodulated output. Okay, so I hope things are falling in place and you have fairly good understanding of how this stagger tuned balanced frequency discriminator works. Okay, so this is the basic theory. Okay, now where is our s1 tilde of t? Let me complete this because yeah, it is here, pi times, let me delete this highlightation. Okay, there is a plus term here. Okay, pi times bt small a capital AC times 1 plus 2kf divided by bt times m of t. So this is my s1 of t. Now let me write down this expression here. Pi times b suffix t times small a capital A suffix c. Now instead of minus I have plus 2kf divided by b suffix t m of t. Now you subtract s2 tilde of t from s1 tilde of t modulus. So what happens? When you do subtraction, the DC terms will get cancelled. I mean pi times B A capital AC plus pi BT will get cancelled 2 pi, then small a capital AC KF times m of t minus of this term, the whole term. So this is equal to pi b suffix t a and AC. So this minus into minus, it becomes plus. Let me put minus here, no problem. Again it will become plus 2 pi a AC KF m of t, and this minus becomes plus, and this term will get cancelled. So your final answer is 4 pi a capital AC k suffix f m of t. So this is the output of your system. Now your demodulator output y d of t is 4 pi small a capital AC kf times m of t. Therefore y suffix d of t is directly proportional to m of t. That's how your frequency discriminator works. Okay, so that's it about balanced discriminator. So that's the mathematical theory behind balanced discriminators. So as you can see, the balanced discriminator that we discussed earlier essentially tries to this diagram. Okay, so this is the most basic form of discriminator. Okay, the other improved versions of the balanced discriminator are also available, so you can refer some standard books and you can get some basic knowledge. Okay, so that's about the FM discrimination or demodulation of the angle modulated signal. Okay, that's it. Now let me come back to a point which I mentioned sometime at the beginning of this lecture beginning of this lecture on FM discrimination. Okay, that there is a differentiation involved at various stages, right? So your modulated signal x of t is differentiated, right? So this is a differentiation involved which we have used some form or the other. So differentiation comes with the picture like d by dt of x of t, and because of that what happens, your output envelope will be depend on the derivative. Okay, in fact not only because of the derivative but also because of the term your argument in the cosine function. Okay, for example your x1 tilde of t is going to be a times your derivative of your input signal in the complex time domain plus j times pi of b suffix t x tilde of t. So this is what we had. Okay, both these terms you can see that if the input signal itself has envelope variations, this one, okay, they will be either passed on as such to the output, or worst still they will be extenuated because of the derivative operation. Okay, sometimes even though the envelope variations themselves will be small, the rate of variations sometimes may be quite large. Okay, see if you take cos omega ct now and a of t, the magnitude is varying. Now if you, let's say this is my x of t, if you take derivative then you have to take uv dash plus u dash v. Even though the amplitude is varying very small, the moment you take derivative then it becomes very large. Okay, similarly let's say cos omega ct, if you take derivative then what will happen, you times omega c times cos of omega ct, where fc is let's say 90 megahertz. So therefore it becomes very very high because of the 90 megahertz carrier frequency. 90 megahertz and times 2 pi times 90 times 10 to the power of 6 times cos omega ct. So therefore once you take the derivative, because of this multiplication it becomes very large. So therefore the envelope becomes very big. So that's what we are saying. See, originally I have the frequency modulated signal like this. Due to some noise there will be some small variations like this, like this, like this. Even though the variations are small due to noise, the moment you differentiate, then it will be amplified. I mean it will be big. The rate of variations may be quite large the moment you differentiate, and then they can be extenuated. So your output in that case will be proportional to not only m of t as it should be, it is also proportional to the derivative of this guys. So for that reason what did we say? We said pass it through the limiter, right? Recall this operation. We said pass it through the limiter. Output of the limiter is like a square wave, you will get it, and then this is again given to the bandpass filter, and that bandpass filter output is a pure constant sine wave. Okay, if the input signal does not have a constant amplitude, I mean if it has an envelope of its own, it has its own time varying envelope like this time varying envelope, then these variations will be passed on to the output also, which we don't want. Okay, we want purely on the argument of the cosine function. Okay, your modulated signal is a times cos of omega ct plus phi of t. What we want is our output should be purely depends on this argument. We don't want any dependency on the amplitude. Okay, therefore the balanced discriminator that we have discussed so far is sensitive to this amplitude variations, if at all has some variation. So that is a of t. If there is no sensitivity, then you can simply write a times cos omega ct plus phi of t. If there is some, this is pure fm, and this one is pure fm plus noise. If noise adds, here the noise is additive noise. So that is why the noise is sitting on top of this waveform, and the bottom also like this. Some waveforms are sitting. So that is something that you must appreciate. So even the balanced discriminator, whether it is balanced or unbalanced, it doesn't matter. The kind of discriminator that we have discussed till now are sensitive to this amplitude variations. Okay, see, my balanced discriminator should be sensitive to the argument of my cosine function, but now what is happening, it is sensitive to the amplitude variations also, if the amplitude is not constant. Okay, so the balanced discriminator is sensitive to amplitude variations of the input signal. Okay, therefore what is the remedy? Put a band pass limiter. Band pass limiter means what? You have hard limiter followed by band pass filter. These two blocks together called a band pass limiter. Okay, in one of the lecture I gave you an intuitive feel of how does the bandpass limiter work and what does it do. Okay, now let us develop a slightly better understanding of that. Okay, basically to polish off our discussion on FM demodulation, because this bandpass limiter is a very important block in the frequency discriminator, almost an essential component of the FM demodulation. Okay, so In FM demodulator, we need this bandpass limiter. Otherwise, demodulating your FM signal will be very difficult. Therefore, before you pass the FM signal for the demodulation, that means your d by dt and envelope detector, you must pass it through the bandpass filter. Okay, so the purpose is to convert the input signal into a constant amplitude signal. So a of t cos of omega ct plus phi of t to a times cos of omega ct plus phi of t. So that is the purpose of your bandpass limiter. Okay, so input signals which may have some envelope variations, and that envelope variation is denoted by a of t. And this envelope variation comes due to distortion. Okay, some distortions introduced by the system, distortions by system itself, or noise. Okay, otherwise it will be a only. Okay, whatever the reason it is, we like to kill if there are any amplitude variations present. Therefore, we like to kill these amplitude variations, and at the same time we like to get FM signal back intact, and that's what a bandpass filter does for us. So if you so this is the block diagram of your bandpass limiter. Okay, bandpass limiter followed by your FM demodulator, d by dt times d by dt followed by envelope detector. Okay, so the bandpass filter is tuned to this bandpass filter is tuned to the carrier frequency Fc. This limiter and the bandpass filter as a whole is known as bandpass limiter. So the input to this, which not only contains your angle modulated signal, but also the instantaneous amplitude A of t. Okay, A of t is the instantaneous amplitude because it is a function of time. Okay, but actually it should have been a constant value. So, but it is not now. So the input may have some temporal variation. Okay, may have some variation with respect to time, which we want to kill. Because if you don't do that, then what will happen? You are giving to the d by dt. So you are taking the differentiation of your a by a of t. Okay, and this a of t will appear in the output, which we don't want. Okay, therefore the bandpass limiter produce an output time, let's say a dash times cos of omega ct plus phi t. Okay, we would keep our FM signal intact. So afterwards, no, you will get a square wave signal like this, and that signal will become a pure sine wave. Okay, but the bandpass limiter eliminates the amplitude variations. So that is the whole important point. Now let us discuss the whole concept a little more rigorous mathematics. It is a simple theory, okay, but let us go through it because it is important to have a very clear feel for these things. Okay, so let us start with the hard limiter, or you can simply call limiter. Why is it called a hard limiter? I will tell you. Okay, the hard limiter is a device, as I mentioned, is something like a highly saturated amplifier. It's basically an amplifier, but it is highly saturated amplifier. Okay, or you could say it is a clipping circuit which clips at 0. The characteristics would be like this. Let's say plus 1, and this one is minus 1, and this is my Vi, and this is V0. So this is the input output characteristics of your limiter. And hard limiter. Okay, so you have a hard limiter and it is a highly non-linear system. Now what about your differentiator? If you want to plot the output versus input characteristics of like output voltage versus input voltage on an instantaneous basis, Then for an amplifier it should be a straight line. Okay, but now here we have a non-linear system. This is a linear system. Basically your amplifier operates at the linear region. Okay, so if the input is even slightly positive, let me enlarge. If the input is slightly positive, the output becomes a constant value, let's say plus 1 volts. Okay, if the input is even slightly negative, let's say very slightly negative, this point, then it becomes a negative voltage. So this is the definition of the hard limiter. As against soft limiting, there is one more limiter, that is soft limiting. It is not the curve like this, it goes slowly like this. It is my soft limiter. It takes very hard decision. It doesn't matter whether the input is 1 volt or 0.0001 volt, it always gives the plus 1 volt in the output. So that's why this is called a hard limiter. Okay, it also limits ultimately, but doesn't limit the moment the signal becomes positive or negative. It carries out the operation more smoothly in the soft limiter. But here as soon as it becomes positive, then it becomes plus 1 volt. So in our case, what we are saying is input Vi of t, let's say this is my Vi of t, is what is our Vi of t? Vi of t is equal to A of t times cos of omega ct plus phi of t. What is my phi of t for the FM signal? Phi of t is omega ct plus 2 pi kf integral of m of tau d tau, this one. Okay, so Vi of t is the input to the system. We can think of the output now as a function of phi, not with a time or with a phi of t. Okay, because the input is a function of phi. Okay, now the input is a function of phi, we can think it like that. So think of for a moment the input is not a function of time but as a function of this variable phi, therefore Vi of phi. Okay, for the time moment, for the time being. So I will tell you why we are considering this kind of statement. Let us assume that Vi is like Vi is, even though it is function of time, let us for the time being let us assume that it is function of phi. So this is a slightly subtle point, okay, please try to understand this. But what is your phi of t? It is this form, omega ct plus kf times 2 pi kf times integral of m of tau and d tau. So this phi of t depends on time here. Phi of t depends on time. Now what I am saying is Vi is a function of phi and phi is a function of time. So indirectly your Vi is function of time, but we are considering in our analysis like Vi is a function of phi and phi is a function of time. Okay, so let's say there is a parametric relationship. Okay, and we also assume that A of t is always non-negative. One more assumption. So Vi is function of phi and phi is function of time and A of t is always non-negative. These three assumptions we are making now here. Okay, therefore what is your Vi of t? Vi of t, we said Vi of t is equal to A of t times cos of omega ct plus phi of t, that's what we said initially. Now based on this assumption, this Vi of t becomes now Vi of phi now is equal to A of t is always positive, so cos of the whole thing I am replacing by a constant phi, not constant phi, that's it. But this phi is function of t and function of phi of t. Okay, now let us try to understand this function a little bit. So this is the transition I am doing here, so please remember that. So a of t I am writing as it is a of t, but this whole argument I am writing as a phi, and this phi is again function of time t. Therefore this phi is equal to omega ct plus phi of t, and phi of t we know what it is. Oh my god, okay, no, this is not phi of t, will not come, this is simply phi of t, I am sorry. 2 pi kf m of tau d tau, I did a mistake. If it is live class you can correct me. Okay, this is a recorded lecture, I have to go back and I correct on my own. Okay, fine. Now what I am saying is, like this phi is function of omega ct plus phi of t, and this phi of t is again 2 pi kf times integral of m of tau and d tau. Therefore I am simplifying the notation using parametric relationship. So vi of phi is equal to a of t times cos of phi. You can ask me, why can't you change this time function? We assume this is always positive, so it doesn't matter. Okay, now we would like to understand what is my v naught as a function of phi. Okay, so you have the limiter, and the input is vi of phi, and I would like to find out what is v naught. So what you are saying is v naught is going to be equal to plus 1 or minus 1. Okay, plus 1 if vi of phi is greater than 0, and output is equal to minus 1 if vi of phi is less than minus 1, because your hard limiter is like this, vi, and this is v naught. Now I am plotting, instead of vi I am plotting in terms of phi. Okay, this is my v naught of phi, or let us say vi of phi. Okay, so what we are saying is v naught is going to be plus 1 if vi of phi is greater than 0, and it is minus 1 if vi of phi is less than 0. Now we can ask a question, when will this vi of phi is greater than 0? At what condition it will be greater than 0? Because your vi of phi is equal to a of t times cos of phi. Now we said this is a constant, a positive constant, leave it. Okay, so this becomes greater than 0 if cos phi is greater than 0. So essentially whether vi of t is positive or negative will depend on whether cos phi is positive or negative. If cos phi is positive, then let me write down cos phi is positive, positive cos phi implies positive vi of phi. As long as cos phi is positive, your vi is positive. If vi of phi is positive, then v naught of phi is plus 1. If negative cos phi implies negative vi of phi, and this results vi of phi is equal to minus 1, negative. Okay, therefore what does it mean? If the input is even slightly positive, the output becomes 1. If the input is even slightly negative, the output becomes minus 1. That is the definition of the hard limiter. As against hard limiting, we said a soft limiting also. Okay, so it is not like as hard as your hard limiter. Therefore, now let me write down my output as a, V naught of phi output is equal to 1 if cos phi. In fact, let me write down one more step so that you will understand in a better way. Vi of phi is greater than 0 and minus 1 Vi of phi is less than 0. Now this Vi of phi in turn depends on cos phi. So this I can equivalently write as V naught of phi is equal to 1 plus 1 and minus 1 if cos phi is greater than 0 and cos phi is less than 0. That means what? Half of the cycle your cos phi is positive and half of the cycle your cos phi is negative. Okay, so for the time moment we are forgetting about the temporal relationship. We are not bringing any time parameter here. We are talking in terms of phi and in terms of parameter phi and the output. Okay, so now what can we say as a function of phi? See, this is my cosine function like this, 0, pi by 2 and so on, cos 0 equals 1. So in this range, this is my phi now and this is my cos phi. Now during the positive half cycle, the cos function is positive, so therefore your V of t is 1. During the negative half cycle, your V of t is minus 1. So in this region it is positive and then it goes like this. Okay, so this is my phi. My phi is between minus pi by 2 to plus pi by 2, it is positive. If it is between pi by 2 to 2 pi, then it is negative. Then again 2 pi to, is that correct? This is 3 pi by 2, right? It is pi you are adding. It is 3 pi by 2. And if it is 3 pi by 2 to this point, then again this is positive and so on and so forth. So therefore you have phi here. Now look at this expression. It is periodic with respect to phi. Okay, so it is periodic because cos phi is an periodic function. Okay, it's a function of periodic signal. So this has dependence. Your V naught of t, V naught of phi has a dependence on the nature of cos phi. So cos phi is greater than 0 for half the time. Okay, that is phi goes from 0 to 2 pi and it is equal to less than 0 for the other half of the time. Okay, for a cycle, like half of the cycle it is positive and half of the cycle it is negative, and again for half of the cycle it is positive and half of the cycle it is negative. So this total duration is 2 pi. Okay, therefore half of the cycle cos phi is greater than 1 and for other half of the cycle cos phi is less than 1. Therefore phi goes from 0 to 2 pi. So in as much as cos phi is a periodic function of phi, so V naught of phi is also a periodic function. See, this is my V naught of phi. V naught of phi is also my periodic function, output of my hard limiter. Okay, so this is my V naught of t. So V naught of t, it's a square wave, periodic square wave. So in earlier class we said it is a square wave but frequency modulated square wave, but we are plotting against phi, okay, not with respect to time. Okay, therefore that is a subtle difference, please understand that. If we plot this function as with respect to time, it is not periodic. Sometimes it will be small square width like this, like this. So this is not periodic. But if you plot against phi, then it is periodic. Therefore, I'm sorry, again I'm writing wrongly. V naught of phi is a periodic square waveform. Square wave function of phi. What is the period? Of course, your cosine sinusoidal signal has a period of 2 pi. So therefore, this is essentially a square waveform. Okay, mind you, I am not plotting this as a function of time. I am plotting V naught of phi as a function of phi. Okay, we are not caring how phi depends on time. Okay, we don't, because we said phi is equal to omega ct plus 2 pi kf times integral of minus infinity to m of tau d tau. Okay, we least bother about this, what is happening here. What I am saying is, my phi is after all it is an argument of your trigonometric function, right? This argument is changing from 0 to 2 pi to 4 pi and 4 pi to 6 pi and so on and so forth. Now I am talking in terms of phi. What happens 0 to 2 pi to 4 pi, 4 pi to 6 pi. Okay, so this is a separate issue. If you try to plot time versus your output, that is separate issue. So we are not considering that now. So we are plotting in terms of phi. So as far as phi is concerned, it is constant. Okay, we don't even have to worry about it. Okay, it is not. No, we are not talking about your time dependence. Okay, in fact, we are not worrying about what a of t is. We said a of t is positive. Okay, it is a simple scalar multiplication. Okay, we are not. We are worrying about what is v naught of phi as a function of phi. Okay, so therefore, v naught of phi will not have any dependence on a of t. Okay, so it will have dependence only on cos phi. Cos phi, and cos phi is greater than 0, your v naught of phi is 1, and in that case your a of t just disappears from the picture in our consideration. It is absolutely of no consequence. So this is an important point. So this is a function, your v naught of phi is a function of phi, which is a square wave with a period of 2 pi, and therefore I can represent this v naught of phi in terms of Fourier series, because you have a square functions, right? Square functions with a periodic 2 pi, and I can represent with in terms of the Fourier series. Not as a function of time, please remember, as a function of the phase. Okay, previously we got Fourier series for time functions. Now we are going to find the Fourier series as a function of phi. Okay, and I know what kind of Fourier series a square wave function has. It contains only odd harmonics of the argument, and that precisely, okay, and that is the precise representation. Okay, therefore my v naught of phi output voltage is a square wave, and that square wave is written in terms of Fourier series like cos phi minus 1/3 times cos 3 phi, all odd harmonics, plus 1 by 5 sine of 5 phi minus, and so on and so forth. Okay, so this is the Fourier series representation of v naught phi. Fourier series representation of v naught of phi. Now let us substitute for phi now. Okay, what is phi? Phi is the function of time. So your phi is equal to, we said omega ct plus phi of t. So omega ct plus what is your let me write down here so that phi is equal to omega ct plus phi of t. So this is omega ct plus 2 pi kf times integral of m of tau d tau. Okay, so this is my phi. Substitute this guy into this Fourier series expansion. Okay, so this is 4 by pi. I am bringing the time dependence back now, okay, by substituting for phi. So 4 pi times cos of omega ct plus integral of 2 pi kf integral of m of tau d tau, right, minus 1/3 cos of 3 phi. 3 phi means 3 omega ct plus 3 times 2 pi kf becomes 6 pi kf integral of m of tau d tau plus and so on so forth. Okay, now you can think of this as a function of time now. Okay, so this is my v naught of t now. So I am bringing back to the time dependence. Now because this is the function of time, so instead of saying v naught of phi, I am writing this v naught of phi as v naught of t, because the time dependence is very explicit in this expression. There is time, here also time, and everywhere time is there. So that's what we have now. Okay, so this is the series representation of the output signal at the output of the hard limiter. Now what are we following it up with now? This is my v naught of t, my hard limiter, output v naught of t, input is your x fm of t. Now this is given to what? Your band pass filter tuned to the frequency fc. Okay, so we are following it up with a band pass filter and tuned to the frequency fc. So as we can see, all other components of the Fourier series, 3 omega ct, this one, 3 omega ct, and let me write down complete, put one more series, minus 1 by 5, minus or plus, plus 1 by 5 cos of 5 omega ct plus 5 times 2 pi 10 pi kf integral of minus infinity to t m of tau d tau, right, minus and so on. So you have omega ct and then 2 omega ct, right, sorry 3 omega ct, here omega ct, 3 omega ct, 5 omega ct, this is t actually, t, 5 omega ct, and then keep on goes. Now all these frequencies are given to your band pass filter. Okay, and this band pass filter is tuned to fc. Now what will happen? The remaining frequencies 3 omega c, 5 omega c, and so on so forth will be rejected by the band pass filter. Okay, so if the bandwidth is sufficiently small, then what will happen? Only the frequency which is centered around fc will be passed through this, and the higher frequency components 3 omega c, 5 omega c, 7 omega c will simply removed by this band pass filter. Therefore the output of your band pass filter will contain only this component. What is that component? That component is 4 by pi times cos omega ct plus 2 times kf integral of minus infinity to t m of tau d tau. That's the whole idea of this exercise. So therefore the combination of your limiter and the band pass filter removes any amplitude variations, and it gives only a constant amplitude frequency modulated signal. That means a pure frequency modulated signal. So this is the output after band pass filter. So as you can see, the independent of what is the value of A of t, there is no A of t term here. The output has a fixed amplitude equal to 4 by pi. And your FM signal has 0 variations. Okay, so the FM variations remain your amplitude has 0 variations. Okay, but the argument remains intact. Okay, so it is not disturbed. Okay, so FM variations remains intact as before. Only the amplitude is changed to 4 pi. That's it. Okay, so I hope now with this discussion it is clear how the bandpass limiter works. And it should also be clear that an overall FM demodulator must contain both these devices, bandpass limiter followed by balanced discriminator. Okay, so this is my overall FM demodulation. Okay, it must first contain a bandpass limiter followed by a perfectly balanced discriminator, and together they form your FM demodulation. So let me draw this diagram in detail now. So your received signal XR of t, it is given to limiter, hard limiter, and this one is given to a bandpass filter tuned to the frequency FC. And now in the balanced demodulate discriminator, I have two bandpass filter 1 tuned to the frequency, let's say F1, and this one is envelope detector 1. The lower arm I have bandpass filter 2 F2, and this one is envelope detector 2, and this output is plus minus, and this is my final message signal. Okay, so in fact many of the advantages of an FM signal that we will talk about a little later, particularly it increases the tolerance to noise, which comes from the fact that the demodulator is preceded by the band limiter. Because of this band limiter operation only, this advantage has come. Okay, without this, those advantages will not be available. Okay, so your FM signal is gives very good performance against noise. Okay, it increases the tolerance to noise. So without your band limiter, you cannot achieve the tolerance against noise. Okay, so that advantage will not be available. Okay, otherwise people will never go for frequency modulation. So in the frequency modulation, we get very better clarity against noise. That clarity is obtained because of this band limiter. So the band limiter plays a vital role in your frequency demodulation. Okay, so without your band limiter, you cannot achieve those advantages. Okay, and of course it is required and a necessary component for proper FM demodulation, particularly in the presence of channel imperfections. Okay, if the channel is imperfect, then if the channel is perfect, then we don't have this band limiter. Okay, hard limiter followed by bandpass filter. If the channel does not introduce any distortions and there is no noise added to the frequency modulated signal, then no need of this guy. But in practice that never happens. Okay, so whatever you transmit, that signal will be either distorted by the system itself or the noise will be added, and the noise is coming from the channel. Okay, so if the channel causes no amplitude distortion, no envelope variations of the input signal, then we don't want this guy. Okay, we don't need a bandpass limiter. But invariably channel will impose some distortions, and it will include some noise, and therefore there will be some amplitude variations. Yep. Okay, therefore we need to have a bandpass limiter. We must have a bandpass limiter to achieve these advantages. So I think the principles of FM discrimination and bandpass limiter are sufficiently clear now. Okay, so we have not gone through the complete list of your FM demodulation as such, because we have discussed so far is one class of FM discriminators, which are basically open loop system. Okay, there is no feedback from the output. This is my output, there is no feedback. Therefore this type of FM discriminators is called open loop discriminators. Okay, open loop discriminators. Okay, so there are systems in which we are trying to devise a circuit such that the output is the output is dependent on the input frequency deviation with respect to the center frequency. Okay, so this type of discriminator is called as I said, open loop discriminators. Okay, and it seems that if I say open loop, then the opposite is closed loop. So we will have a closed loop FM demodulators also, and this closed loop FM discriminators is called feedback discriminators. Feedback discriminator, or we can say demodulator. So that we will discuss in the next class. Okay, so till now whatever we have discussed, that all are falling under the category of open loop frequency modulation discriminators. Okay, because there is no output from, there is no feedback from the output to the input. Okay, so in the next class we are going to discuss the closed loop frequency demodulator, that is called feedback demodulators. Okay, let me stop at this point. Thank you very much.